Okay, hi everybody. Our chairperson, Professor Chiranjeev, would have loved to be here to say a few words about the Women in Computing event and welcome everyone. Unfortunately, he could not be here today due to unforeseen personal commitments, so I would like to welcome everyone. The Women in Computing event is part of the CSA Golden Jubilee celebrations and aims to celebrate the work done by women computer scientists, initiate conversations about diversity, to create an ecosystem to encourage and support academic and professional opportunities for women in computing. So far, we have had wonderful talks and panel discussions as part of this series. And today we are very happy to have Professor Manuela Veloso with us to give the concluding talk of the Women in Computing series. I would like to briefly introduce our speaker today. Professor Manuela Veloso is the head of JP Morgan AI Research, which pursues fundamental research in areas of core relevance to financial services, including data mining, cryptography, machine learning, explainability, and human AI interaction. JP Morgan AI Research partners with applied data analytics teams across the firm, as well as with leading academic institutions globally. Professor Veloso is on leave from Carnegie Mellon University as the Herbert A. Simon University Professor in the School of Computer Science and the past head of the Machine Learning Department. With her students, she has led research in AI with a focus on robotics and machine learning, having concretely researched and developed a variety of autonomous robots, including teams of soccer robots and mobile service robots. Her robot soccer teams have been RoboCup world champions several times, and the Cobot mobile robots have autonomously navigated for more than 1,000 kilometers in university buildings. Professor Veloso is the past president of AAAI and the co-founder, trustee, and the past president of RoboCup. Professor Veloso has been recognized with multiple honors, including being a fellow of the ACM, IEEE, AAAS, and AAAI. She is the recipient of several Best Paper Awards, the Einstein Chair of the Chinese Academy of Science, the ACM Autonomous Agents Research Award, an NSF Career Award, and the Allen Neville Medal for Excellence in Research. Professor Veloso earned a Bachelor and Master of Science degrees in Electrical and Computer Engineering from Instituto Superior Técnico in Lisbon, Portugal, a Master of Arts in Computer Science from Boston University, and Master of Science and PhD in Computer Science from Carnegie Mellon University. It is a pleasure to have you with us today. Over to you.
Thank you very much. Thank you all for being here. And I'm going to tell a little bit about AI, so in finance, and then we'll leave some time for questions, and let's start from there. So I'm going to share my screen, if that's okay with you, and let me just try to do this. So there we go. I'm going to share my screen, and basically, and then let's start. So let me just explain to you what I'm going to do, and then I'm going to explain first a little bit about AI in general. So AI, as you know, and I'm sure surrounded by these AI as artificial intelligence, you should know that AI is a young science. In some sense, AI is a science that it's not like, I don't know, chemistry or mathematics or biology. There are sciences that have been developed for many years. AI is connected with computers. Computers basically are devices from the early 20th century. And eventually you get to a point where in the history of these computing in which people wonder if the computers can do more than just number crunching. And basically, Alan Turing in the 30s conjectures that computers could think like people. And then there is this major kind of like event that takes place in 1956, which is the one that I'm highlighting here, in terms of like a group of people, a group of researchers proposed to have a 2 months, 10 people study on every aspect of learning or any other feature of intelligence to be so well described that actually a machine can be made to simulate it. So they thought that in some sense, in 2 months, they would be able to understand every aspect of learning and any feature of intelligence to have a computer really do the artificial intelligence in 2 months, 10 man study. So it of course didn't happen like that. I mean, but it was the beginning of artificial intelligence. And in fact, it's the first time the term was used. Artificial intelligence was in 1956. And the 10 people who were actually invited to this event, which we call the Dartmouth Conference, the summer of 1956, were these 10 names here. And both Herb Simon and Alan Newell were professors at Carnegie Mellon, where I've been for the last 30 years. I got to Carnegie Mellon in 1986. And so, you know, it has been a long journey at Carnegie Mellon. And I would like for you to understand that this is a discipline, this AI, that is young, but very ambitious. But because of the aspect of these, every aspect of intelligence, AI is a science of components. I mean, it's like all the abilities of humans, like natural language processing, speech recognition, machine vision, all sorts of like decision making, you know, the ability that we have to represent knowledge, to learn, to plan, to search, to optimize, and eventually the actual execution, the actions. We can go and do things. So these AI has these components in data processing or perception, in decision making or cognition, and in action or execution. So this is why many of you, or many of us who follow research in AI, this is why we work in components. Now, the integration of all these parts is very important. And in particular at CMU, during my life, I've worked a lot on autonomous mobile robots. There are examples indeed of things that have like perception, so cameras that process data, cognition, which are code that runs on a computer, and actuation because they actually can move given their wheels. And here is a full autonomous robot, mobile robot, moving in the corridors of the School of Computer Science at Carnegie Mellon University in Pittsburgh in the USA. So, and I will keep this in mind. You need to keep this in mind because ideally, when we think about integrated AI, it might not be a robot, but it may be other software that puts together the execution, the decision-making, and the perception. And here is Joydeep Biswas, who actually was one of the main developers of these cobot robots. But it's not, I'm going not to tell you about robots. So I told you a little bit about AI being this young science and explaining the components and explaining that they can be integrated, and gave you an example of these autonomous robots as an example of the integrated AI. I'm going to just give one example of examples of core machine learning, because machine learning is one of the main components of these AI, how do you say, field of science. And then I'll talk about some projects at JP Morgan. So this is the rest of the talk. And you should be free to really ask questions if you want. So I'm going to interrupt for just 1 minute to ask, do you have any questions about the first part of just this general introduction to AI?
If
yes.
if anyone has questions, please post them on the chat, and I will, read them out to Manuela. So
Okay.
maybe there'll be some questions in some time. So you can continue.
Okay, thank you. So let me just give you an example of these kind of like machine learning. So the reason why I want to give you this example is so we have an understanding of what do machine learning algorithms, in particular, we're going to just look at regression from data, actually do. So if you think about these little crosses as being examples of data on some space of a function, so we only have those examples. So now the question becomes, what is the actual model? What is the model that captures all these data? And so one model could be a linear model, and you would try to match a line to these points. And of course, these points would eventually, the line would eventually cover some of these points, but in some sense, it doesn't cover them all. But the lines are very nice because they are somehow very simple to learn the model, because they only have two parameters, ax plus b. So you have a and b, which are parameters that you have to estimate. So you have a model that fits the data. But you might want to have a better model, like a parabola, that now brings three parameters. So there is a trade-off here. The model may be better fitting the data, but it is a little bit more complicated to eventually estimating the three parameters. And then you could have even another model that captures all the data, but problems here may be that, okay, maybe that data was actually not part of the function, was an error, was noise, was an outlier. And so you are here, like what we say, overfitting to the data. You really want to get all the data. And the purpose of building a model is not really only to match the data that were examples of the function, is also to try to have a model that can predict what should be the outcome of the function on points that we have not seen. That's the reason why we try to model the data that we see, is to predict or to assign a value to the data we have not seen. So in some sense, this is another model. And again, this model fits all the data, but it's highly non-smooth. And why is this so interesting to compare the blue and the yellow curve? Is that from the point of view of matching the data, both of them match equally the data. However, blue makes an assumption that what we did not see, or the points for which we don't have data, kind of fall smoothly in between the data we've seen. So there is an assumption here of that the data being sampled is representative of the complete data of the function. So this one here is just very, how do you say, assuming that it's an hypothesis that the model would be like this. And if it were like that, the data we have received was not really illustrating the model well, because it's not illustrating these up and downs, this lack of smoothness between the data points. So there is this thing about overfitting. There is this assumption about like the model being of different level of difficulty, estimating these yellow curve. It's a model also that from a mathematical point of view would be hard to represent. So which parameters to capture this yellow curve? So definitely maybe, so computers now, basically when they try to model data, the algorithms to model, to learn a model from data, you maybe face the question whether it should be like the line, the parabola, or the higher order polynomial, rather than trying to fit this particular kind of like crazy function. So, but the reason why I think that it's important for you to understand, and I don't know exactly the research you do or the developments you do, is that you need to understand that the computers are trying to match a model to the data, and that requires some search, because here you see the green curve, but maybe they started by thinking like this and then like that, and trying to match the actual parameters of the model to the data is a process of computational effort. And so this is like something. So this is the first example that's what the computer is doing when trying to model from the data. And one thing to also think about is like when you model from the data, there is a model that comes out and is learned, and then the model is used and not the data anymore. So in some sense, the model is going to be a function, the actual analytical function, or a black box that captures the model, and you can use just the model, and you are somehow done with the data after you learn the model. So this is an example. I'm going now to talk about a different problem, which is this model-free learning from data. So we don't learn a model, but you basically learn not also a function of fx, f of x, or f of parameters of input, but you learn to basically find classes in the model, in the data. So here is like an example, and the reason why this is important is because in this example there are basically two classes, one of these little kind of dark dots, and the other one these transparent dots. And the point is that the two classes in this space x1, x2 can be separated by a line, and therefore it's the question becomes, if you commit on separating the classes through lines or planes or multidimensional planar surfaces, which is the best line? So now what machine learning does in this model-free learning from data is to try to find this best line. And if I would ask you which one of these three lines is the best, which one would you say? I mean, can one of you tell me whether H1 is a good line to separate the two classes, H2 or H3? Which one do you think is the best line?
H3.
H3, exactly. And the reason why it's H3, so there is one that is definitely not good. Which one is the one that's definitely not good? Which one is the one that is really not a good separator?
The first one.
H1. So it's not a good separator because in some sense, it actually, smaller than H1, you have the dark class, but then larger, you have a mixture of dark and transparent. And so it's not really a good separator of the two classes. But H2 is problematic because H2 also separates the two classes. But beautifully, the answer was H3 because in some sense, H2 is risking a little bit the generalization. And H2 is is very close to this a dark kind of dot and very close to these transparent dots. So it's really taking like this break here, which also separates, but there is more potential error in generalization because if you now have a dot here, if you now have a dot there, it's so close to the boundary that if you compute mathematically the error and the distance between these line and the closest points or the other elements of the class, you are going to see that hypothesis is not as good as this one that has a much larger distance to the classes. So I'm just saying here with words, the computation that somehow the learning algorithms do to find their best separator, okay? But there are things that are very hard to separate with a single line. And here is what I really want you to understand. Suppose that instead of those dark and transparent points, you would have these pink and blue points as the examples of two classes in just a one-dimensional space here, very simple. So I can ask you, how do you separate these two classes with a single line? And you can try, and if you try putting one line here, well, it's not a very good separator. It does separate the pink to this side, but on this side, it didn't separate the pink from the blue. And here, you might also think that you can separate, but you can't. So my question is, how do we use a line, a straight line, a single line, to separate these two classes? Does anybody know how to do this and what is the magic here? So the magic here is the following. So we have the data and we basically transform the data. And if we transform the data to just, in this particular case, multiply the data or transform the data by, not multiply, like we square the data, then there is a line that separates the data. So these you should never forget this example. Is one of the simplest examples for you to understand this concept of applying kernels to the data, applying transformations to the data, and being able to massage the data such that the classes are linearly separable. So the point is that you need to understand that, how can I say, separating classes that don't seem to be separable the way we look at the data is the job of the machine to really try to separate by transforming the data. So the concept of a neural net, it's also, for example, this is the example, the famous example of XOR, two classes that cannot be separated with a single, in the two-dimensional example that I just gave you, with a single line. And then a neural net is in fact a way to get as input the value XY here, or the input, and makes transformations, multiplications, thresholding, sums, makes transformations such that magically, one way or another, those transformations lead into data of the two classes that is separable, that can be separated. And in fact, that's the secret of deep learning. Deep learning is about giving input data, having as output separate classes, and basically using all these nodes that are in between the input and output to transform the data in a way that you add this feature with that, you compare, you do this, you do that, on many layers, in the way that exposes how the data, the input data, is actually separable, or is actually, you can identify the parts of the data that are associated with which one of the classes by transforming the data and being able to have the machine search for those transformations, and eventually you separate the classes. Okay, so the reason why this is very important for you to understand, because it's this example illustrates the basic transformation you can think, and then this can grow crazy to transformations of this nature. And the computing AI is indeed about searching that space of transformations that can lead into the separation of the classes. Okay, so before I talk about the projects, I'm going to stop here because I will be happy to take questions about these specific kind of two thoughts on machine learning. One, learning a model from the data, and the problem of actually hypothesizing or trying to find which function should we use to model the data. And the other one is about classification. How do we find how to break data into multiple classes? And instead, the techniques are about massaging the data, transforming the data, stretching the data, such that these boundaries between the classes, between the features of the data, become separable. So you multiply by these, you multiply by that, you do this, you sum, you add, and then whoops, this space becomes separable. Is that clear?
Any questions? Yeah, there is a question for 1 second. There's a question from Akif who says, why can't we use two pieces of straight lines instead of a parabola?
That's a very good question. So you could, but if that would be the case, I can also find examples for which then two pieces, two lines would not be enough. So in some sense, you can, no matter what you come up with the hypothesis, it's still the case that if you fix that hypothesis, one line or two lines, there is an example for which the two lines are not enough, and you have to transform the data so that the two lines now are able to do it. So the question is not one or two lines, or it's whatever hypothesis you come up with, you may not be able to use that hypothesis without without transforming the data. You understand? So that's the and the reason why this is interesting. And in fact, the question also could be, maybe we can try like this. Okay, so we can have multiple hypotheses, like one line, two lines, three lines, transformations, and then the machine learning algorithm tries to see one line is not possible, two is okay, or it's still not okay, and eventually you start moving in this. So you move in this space of hypotheses at the same time that you are trying to separate the data. So there are here two conflicting goals, which is you need to separate the data. So the data is an input, but you don't know how to separate the data. So it's this joint kind of like, let me see if I try just one line, can I separate? No. Okay, what if I now transform the data and I do the parabola, or I do this? Oh, can I still use one line? Maybe not. And then you move in these two spaces, trying to separate. The goal is to separate the data. And I was giving an example for which the choice of separating the data involved transforming the data. Okay, very good question. Any other questions?
So I have a quick question. When you transform this data, there has to be some notion of consistency with what the data actually represents. So is that concern? I mean, how do you ensure?
Very good question. In fact, this is a deep question one way or another, because these transformations, imagine if you raise this feature to the square, you stretch this thing, the age of the person, you multiply by 25, and you add I don't know what, and so you can do things to the data that become separable, but then it becomes very obscure. What is the meaning of all these transformations? So this is why many times, especially in neural nets, you are able to separate, but you really don't understand why is this thing of one type and these of another class with this feature. So it's almost as if, think about, you are like trying to learn from images cats and dogs, or here like the neural nets were able to identify bicycles and chairs and persons and all sorts of things, but it's not very clear why this is a person. So because exactly what you were saying is, we are free to change the data in any way, then the transformations that are made to the data do not have a lot of like meaning, and therefore that's why people say that sometimes machine learning is a black box, because it's able to separate, but you cannot really say what are the features of that class anymore, because the transformations are very cryptic. Okay, it's a very good question. So the goal is always to have the machine be able, the AI system, machine learning system, be able to separate the classes, but it's hard also to combine it with transformations that have a meaning. Okay.
Okay, thank you.
Okay, let me pursue here and now just delve into these projects. And I literally just a few times, so I'm going to probably skip some of the projects, but I want to give at least one example of a project. So now I'm going to give you examples of projects in the world of AI and finance, in particular within the scope, within the world of JP Morgan Chase, which is a very large, how do you say, institution, a very large industry, a very large operation that involves a lot of data, a lot of people, a lot of problems related to large sets of data, large sets of customers, large sets of markets. Everything is lots of data in the millions. So that is overwhelming many times from an AI point of view. And I'll tell you an example that I'll just focus on a few projects, but one of the examples of things that we've done with JP Morgan Chase has to do with the fact that so people are traders, they trade assets. There is let's talk about stocks, but equity, so a stock exchange kind of like market, and the functions involve knowing how the stock varies, the price of the stock varies, and then making decisions on whether this is the time to buy the assets you have or to sell to buy assets of that particular kind of at that price, or to sell the one you have. So think about buying and selling your house, but here is particularly the actual stock market. So when we were talking about this, as you see, these decisions are made based on many images of how this time series data is changing. So when we looked at these, I thought that this was about making decisions that are based on images. And so we looked at these screens and we converted them into images, given that we knew that neural nets could be very good at separating classes, even if they were complex. So we basically used the data in a time series. We broke into small images of little chunks of these time series evolution, and we assigned values of buy, no buy. So instead of being person and chair and bicycle, it became two classes, the class of buy and then the no buy. And every time that there was in the data, when the actual human executed a buy, then you had this little image of the signal, how it was changing, and we associated that image with the classification buy. And then if by any chance, and this is another example of buy, and all the others were examples of no buy. So all these are examples of buy. And so we were able to train a neural net, and instead of using examples of people and chairs and apples and orange or objects or cats and dogs, you really use this image of the function changing in a way that the label, the classification, said that this was a buy example. And here is another one that says it was a no buy. And we are able to such a training of these, using these images that capture the decision making of these two classes by no buy, we were able to match what humans have done with 95% accuracy. So this is an important result in terms of saying the novelty of trying to bring images that capture decisions. So this was one project, it's the Mondrian project. Now I'll tell you another project and then I'll open for questions. Another project is that somehow the stock market, this New York Stock Exchange, but any other stock exchange would be the same, is in fact, as this is a different problem from an AI point of view, is in fact a very kind of multi-agent system. So it's like many players in this game, and we have built simulations that enable us to capture what these other agents are doing in different levels of strategy, and we can have agents that learn how to perform in these markets by observing the reward they get. We define reward, we define actions, we define state, and we are able to learn. But interestingly also, these multi-agent simulations enable us to generate lots of variations of the actual data of the stock market. So the simulations enable us to learn, to have these agents learn in challenging situations. So this is now a learning example in which you go through these simulations and try to have strategy learning based on many parameters that we adjust. These type of like simulations lead into something that I think is very important for us to know, into synthetic data. So think about JP Morgan or other financial institutions that have a lot of real data, lots of data, but they are basically data that is private, data that is real and not to be shared. And so the problem becomes, how do we do research in this world in which the real data is not available for actually trying to learn a classifier, trying to do all sorts of like, how do you say, understanding of what's happening with these real data. So we created a synthetic data project that is able to generate different types of data. For example, we have done all sorts of data based on anonymization of real data, learned models, and these agent-based simulation that I just saw. And we can have also planning-based simulations. And these data is then available for researchers and for basically a lot of the development and the trying to understand how the AI systems can actually respond to challenging situations. So if you are interested, send me an email and I'll set you in touch, and I'll send you a pointer to the synthetic data, available synthetic data we have. And then also, I don't have time to talk about this for so. And I'm going to finish just by mentioning this very nice project in which, and I think that in which we basically are able to generate automatically PowerPoint slides. This is a little bit like the robot moving around because it's a complete gets input from humans. You actually map to the data and you can generate the actual slides automatically. And here is the video that shows how this works. So this is a demonstration of this AI system that interacts with a human by saying, can I help you today? Create a company briefing. And the human says, create a company briefing deck. And then the AI CFIT, which is the AI PowerPoint, is going to basically look at its slides and based on the language, generates all these slides automatically. And literally the mapping from language to parameters of these slides is done automatically. And then it enables you to also have the user ask for changes of the data. And it changes that, okay, I would like to add something to this deck of slides. And I would like also to remove something from the deck of slides. Or I would like to have the actual duration be just 1 year. And literally all these updates are done automatically by this AI to PowerPoint slide system that is able to reduce to 1 year, add whatever it's needed, and make all the changes. So in conclusion, so we have a variety of other projects. We can learn customer satisfaction, detect and prevent financial crime, regulation and compliance, fairness in markets, ethics and values, client experience. The publications are available, so you can read the publications of our AI research group at jpmorgan.com/AI or at my website at CMU, which also has a pointer to the publications of our JP Morgan publications. And if you are interested, you can send me email at manuelaveloso@jpmorgan.com, jpmorganchase.com, and I'll be happy to consider your interest on AI and finance, and I'll be very happy if you want to have summer internships, if you are considering this as a possible career, please contact me because we are hiring in people that have an interest on AI. And then finance, you may know or not know, but it's the AI part that we are hiring for. Okay.
Thank you, Manuela, for an absolutely
1 minute for questions. Yes.
Yeah, thank you for an absolutely fascinating talk and for demystifying AI for many of us. There are a few questions. Shubham asks, first, how does one allocate limited funds to multiple stocks with buy label?
No, it's a very good point. So let me just clarify that this work we have done, it's really, how can I say, it was really just trying to learn to reproduce the decisions that humans have done. So here is not a question of actually learning to do the right thing, but it was only to do what the people have done. So that's how we did it. Okay.
Okay.
Fairness-related issues, actually, have you explored any fairness-related issues for stock trading? Indeed, we have a huge effort on fair trading. And if you go to our website, you'll see some of the papers there. And this would be a talk by itself. But yes, we are looking at how do we make these much more fair decisions within stock trading, definitely. And I would be very interested. So Shubham Gupta, I believe, sent this question. Please, if you have an interest, also send me email. I'll be happy to send you the paper or put you in touch with Svetlana, who does all that research. Okay. You talked about stock market prediction where the model predicts buy or don't buy. So does the model work in real time? So this is a very good question too, Ravi. So the point is like this. It's actually the case that these work we've done is not truly deployed. So it's not that the current stock market exchange or the actions in the stock market are driven by these real neural net that learn buy, no buy. This was just an example that is not yet being used in practice, okay? But the training is definitely offline, but then the use of the neural net after being trained can be done in real time. There is nothing wrong with just running the neural net on all the different stocks, okay? Vijay, how do you measure effectiveness of the auto-generated charts and slides? Oh, that's amazing. Very good question. So it is something that the effectiveness, it's first the correctness, and the fact that in fact, the pie charts, the graphs are all of that particular kind of like, how do you say, the data is accurately represented. Effectiveness is like what the humans ask for. So the humans are the ones that know, I want a pie chart here, I want the histogram there, I want this type of kind of representation, I want these terms. So the humans are in control. What the machine does is basically, boom, automatically do it like in one stretch. And then people, like you saw in the example, can correct. And if they don't like this format, if they want to add more stuff, they can. So the actual effectiveness is in the human control, and the machine, the AI PPTX, is basically executing what it's told to do. Okay. So Aritra, in the buy no buy problem, why not use a sequential algorithm to represent the portions of the time series instead of images? This is an excellent question, and there is, in fact, no reason not to use the actual time series, the portions of the time series as data to the neural net. And we have done that. But the novelty here is to say, which was surprising from a research point of view, that the image itself also can be used. And the reason why this is important is because then we have used on other types of images that support decision making rather than the actual numbers. So it was very interesting to see that images, after all, can capture, for example, think about images of a pie chart, images of colors, images of displays that capture how people make decisions. So the novelty here was not the handling of the time series per se, but was the handling of the time series as images. And you have to understand, Aritra, that before, neural nets have been only applied to objects. People didn't associate kind of reasoning to images, and objects like a person, a chair, a table, and all these things have been to think about. So this is extending what images can capture. Thank you. I'll look at their papers. Okay, Ravi, thank you. Maria Ma. Yeah, in the chatbot example, what are the underlying NLP techniques that are being used to understand the intent of the user and generate reports? There is here in fact, no extraction of intent. The user really is specific about the changes it needs to be performed. It says, use that deck, and here's I want. I want this company, I want this year, I want this. So it's very specific. No use of intent learning. However, from a natural language point of view, as you are interacting with users, user may use different terms. They might say, do a plot, do a curve. And the AI PPTX actually learns to map terms of the human language to different kind of like outcomes, okay? So that's basically what it's learning. It's learning to map language to thing. Unfortunately, I cannot, I have to stop here answering questions. So I really appreciate this invitation, Bhavana and Shaya. And I wish everybody good luck and thank you very much. And please keep in touch, okay?
Thank you so much for this excellent talk, Manuela. Thank you all for attending. I'm sure you really enjoyed the talk, and this marks the end of our Women in Computing lecture series. And we were very particular that Manuela should give the final lecture and sort of have the last word on this. Thank you so much, Manuela.
Thank you very much. Bye-bye. Thank you.
Manuela. Bye.
Bye. Okay, for the rest of you, I'm sorry, Manuela didn't get to answer your questions. She had another commitment, so she had to leave a little bit early, but sorry about that. Okay, so thank you all for attending. And that's it from CSA Women in Computing series. Yes, okay, thank you.
Bye.